Okay, in this module we're going to do a quick introduction to electric charge. This is chapter 21 in your book, and um, electric charge is going to be a very foundational notion for a lot of what we do through the course of the semester. So I want to make sure that we understand what's going on here. This is all material that I'm expecting you have a fair degree of familiarity with, but just to make sure we're all on the same page, let's get started. The first thing I want to say about electric charge, is sort of a philosophical point, is that this is what we know in physics as an intrinsic property, which is to say that it exists in nature not as a result of other factors, but it exists in and of itself as an identity. So it exists, I think we know, as both a positive value and a negative value, and on the atomic level, the positive value is associated with a proton, and the negative value is associated with the electron on the atomic level. When I say that these are intrinsic properties, what I mean is it's not as though you could take the positive charge off of a proton. Part of the definition of a proton is that it is positively charged. It is intrinsic to the nature of a proton. By virtue of being a proton, it is positively charged. Similarly, an electron must be negatively charged. It's part of the definition of what an electron is. So that's what I mean by intrinsic properties. So we've got the proton and the electron. There are other charged particles out there, but these are the subatomic particles, the things that make up atoms that are charged, that we're generally most interested in. And this is an actual physical quantity. So it's a physical quantity, and it's measured in coulombs, which is abbreviated with a capital C, after this great man, Coulomb, who did so much work in this area. So this is a physical quantity, and it's measured in coulombs. To give you an idea, the amount of charge on a proton or an electron, something known as the elementary charge, so this is E, which is defined as the elementary charge. In standard units, in coulombs, the elementary charge is equal to 1.6 times 10 to the negative 19th coulombs, which is to say the amount of electric charge on a proton or an electron is really quite small. You could take the reciprocal of this and figure out how many protons or electrons you would need in order to get up to a coulomb of charge, and you'd see that you'd need quite a lot of protons or electrons to create a whole coulomb. 1 coulomb of charge would require 6.25 times 10 to the 18th electrons or protons. This, I should have noted, this could be positive or negative, right? It could be positive in the case of a proton or negative in the case of an electron. And since most everyday matter, just about all of everyday matter, is made up of atoms, and atoms are made of protons and electrons, we think of charge as being quantized, meaning if an object has a charge, it has some integer multiple of this elementary charge. So if I took an electron off of you, if you are neutral, and I take 1 electron off of you, your charge would be then positive 1.6 times 10 to the negative 19th. If I took 2 electrons off of you, you'd be double this, right? Positive 3.2 times 10 to the negative 19th, etc. So we think of electric charge in our world as being quantized. Before we talk a little bit more about how charges interact with each other, I want to make sure that we're clear on a couple vocab words that I'm going to use. I'm going to use words like conductors, or we will talk about conductors, and insulators. And just so we know what this is, a conductor, I think you probably do, but just so we're clear, a conductor, this is some sort of material that allows for the flow of electric charge. So allows for the flow of electric charge. And an insulator, in some way, this is a material that inhibits charge flow. So classic examples, obviously, of conductors. Some examples: metals, right, are excellent conductors. Salty water is a good conductor. There are others, of course, but metals are probably the most common example. Think of like a copper wire. Copper is valuable in part because it's such a good conductor. Insulators would be things like plastic is a good insulator, or rubber is a good insulator. Pure water, so pure H2O, is actually a fairly good insulator, not a good conductor. It's only once you dissolve some sort of a salt in the water that the water becomes a good conductor. Most water you find out there in nature, though, does have some amount of salts dissolved in it, so most water is actually a reasonably good conductor, the stuff that you're going to find out there in the lakes and rivers and so forth. Okay, so if we have some electric charges, might be interested to know in how they interact with one another, and to understand how they interact, we can look at Coulombs' law. Again, named after Coulomb, the Frenchman. One thing that I'm certain you know is that there's the basic way in which charges interact with one another is that opposite charges attract and like charges repel. So two protons are going to repel one another, whereas a proton and an electron would attract one another. This is sort of fundamental. And attract or repel, when we use words like attract and repel, we're implying that there is a force, and in fact there is a force, or an electric force. So there is such a thing as an electric force. Sometimes this is called the electrostatic force, but there is such a thing as an electric force. It's a very strong force, much, much stronger than gravity, and it's you can calculate the electric force between two charges using Coulomb's law, which is this old equation that we, I think, have seen before. So the electric force is equal to the electric constant K times the two charges, Q1 and Q2, divided by the distance, the radial distance between them, R squared. So just to briefly unpack this, this is the electric constant K, which has a value of 9 times 10 to the 9th in standard units. Q1 and Q2, Q is our abbreviation for charge, so these are our charges. And R is the distance, and that distance, again, is squared. This equation, we remember, looks quite a bit like our old equation for gravity, which maybe isn't a huge surprise. Similar forces in certain ways. So this is Coulomb's law. That's what this equation is known as, Coulomb's law. It's a way of calculating the electric force between any two charges. All you need to know are the charges, I should say, measured in coulombs, the distance between them measured in meters, and then in standard units, this guy K is 9 times 10 to the 9th. So this is old. There's another way. This is our sort of old way of writing Coulomb's law, and now we're going to have sort of a new way of writing Coulomb's law, which is essentially the same thing, only we're going to write our electric constant K slightly differently. Rather than putting this K in here, we're going to break K down into some smaller pieces. And we're going to call K 1 over 4 pi epsilon 0. So this thing is K. This is K. So this whole thing, 1 over 4 pi times 1 over 4 times pi times epsilon 0 equals 9 times 10 to the 9th. So you might wonder, if we already have K, why do we break K down into these pieces, 1 over 4 pi epsilon 0? We're going to see for certain calculations, having this broken in this way allows us to unpack some interesting relationships. I would instruct you to think about, what is it about this 4 pi? What does 4 pi invoke in your brains? this isn't a random number. There's a reason for this 4 pi. That's sort of interesting. The epsilon 0, by the way, this is new to us. Epsilon 0 is known as the permittivity constant, or the permittivity of free space. Or by free space, I mean vacuum. And this has, I'm not going to get into what permittivity is all about, but it has something to do with the ability of a charge to set up an electric field. And you can look up, there would be permittivities there'd be a permittivity value for air, for glass, for whatever. This is the permittivity of empty space or a vacuum. So that's K. So then we take this whole thing, 1 over 4 pi epsilon 0 times Q1 times Q2 over R squared. And that's our new formulation, or new way of writing Coulomb's law. You could, and it might be appealing to you to sort of combine these terms and just say F electric equals Q1 times Q2 over 4 pi epsilon 0 R squared. That would be another way of writing it, of course. So we're going to try to sort of write it in this way, and just remember that this reduces to the value of K. I want to make some points of interest that will be helpful to us as we some points of interest as we start to think about some problems in class. Let's imagine one really interesting situation is a situation where you have a sphere or a shell of charge. So here I have this shell, and I want to think about this as this is supposed to be some sort of a spherical shell. So this is a charged shell. Charged conducting shell. So we can imagine this is metal, and we'll imagine it's a very, very, very thin sphere of metal. And let's imagine it had some charge on it, some charge Q, and we would like to somehow evaluate this charged shell using Coulomb's law. So maybe we have another Q, so we can call that Q1, and maybe we've got this other Q over here, some little point charge is a point charge. We can call this guy Q2, and we're curious to know how could we establish the electric force between them. It's easy to think about how we deal with a point charge as a point charge, but what about this shell of charge? How do I treat this? Well, you might remember back when we dealt with gravity, we said that if we had a sphere, like a planet, we could treat that whole planet as a single point. We could imagine all of the planet's gravity being concentrated about a single point at the planet's center of gravity. And similarly, in the case of a shell of charge, you could treat this as though it were a single point charge, where all of the charge is concentrated at a single point in the center of the shell. And this is a really important concept. So you can treat a charged shell like a point charge. Like a point of charge at the shell center. I'm just saying this for you. I'm postulating it. I'm not proving it to you. We will prove it later using something called Gauss's law. So that's a couple of chapters away. So we're going to come back to that. We'll revisit this with Gauss's law. So here I could do it. I could take the entire value Q1 and imagine that it's concentrated at that point right there. Just so we're clear, then our R value that we'd be using in Coulomb's law would be that distance from the middle of this shell to Q2. Another thing you might be interested in is what if we had a shell of charge. So here's this charged shell. Here it is. And I'm going to imagine that a shell is hollow. So we have this hollow shell, and this shell has a charge Q1 on it. And then what if I have a little point charge here within. So here's Q2. And I could ask myself, all right, well, if there's some charge on the shell, Q1, and I've got Q2 over here, what force does Q2 experience as a result of Q1? And something that we're going to see later on, I'm again just going to postulate it to you without proving it, but we would see that it turns out that Q2 experiences no force due to Q1. So a point charge, it doesn't have to be a point charge. A charge within a charged shell experiences no electric force. Later on, the way we'll talk about this is we'll say that the electric field E, which we haven't experienced yet, is 0 inside of this shell. We'll talk about that later. That's a preview of next chapter. This again there's a connection to gravity. You might remember we had said previously when we talked about gravity that if you were if you had a hollow planet and you were in the middle of the hollow planet, so imagine that it's not solid all the way through like Earth, but some sort of a planet where all of the mass of the planet is concentrated in the crust. And then you imagine you're in the middle of this hollow planet, and we said, how much would you weigh? Well, we said you'd weigh 0. You would have no weight if you had, so if this was a planet, here's some planet, and it's a hollow shell, and you were inside, your weight, the force of gravity inside, would be 0, which is very surprising. You would float there as though you were in outer space. Turns out it's the exact same mathematical argument for why there is 0 force. So inside here, F electric is 0, which maybe this would be surprising to you, perhaps this is surprising to the little point charge here. So two points of interest that are going to be useful to us as we start to do some calculations using Coulomb's law. So that's a brief overview of electric charge. We'll do some practice problems in class.